In the alternating series video, we talked about how a series can alternate signs, and there is a test to determine whether it's convergence, whether it converges. There is also a comparison that we saw where we had the alternating harmonic series versus the original harmonic series. The harmonic series, of course, is the series 1 over I. The alternating harmonic series has the same terms but alternating signs, both series starting with the positive. And as we saw, these series, one diverges and the other converges. Now, what we also saw was that if we looked at the partial sums, that we saw that the sums always go up by a specific amount. Specifically, they are always increasing in the harmonic series, and that is because we are always adding positive terms together, and every time we have a positive value and add another positive value to it, it gets bigger. But in the alternating harmonic series, where we start by with a positive term, the next term is negative, which means that we actually decrease because we're introducing a negative number with the positive. Now, we remain positive because the idea is that the terms approach zero in magnitude, so each new term is smaller than, or at least no bigger than, the one before it. So when we add in a negative number that is smaller in magnitude, we end up with a smaller positive number than what we started with. But then we add in a positive number again. And then we introduce a negative number after that. So we get bigger because now we are adding a positive number. But it's worth noting again that the number that we added does not get us back up to what we started with. Then again, we introduce a negative term, and that's going to make us decrease. And then we introduce a positive term again. And it increases. Now, for comparison's sake, if we write these all with the same denominator, we start out at 60 over 60, then we drop to 1/2, or 30 over 60, then we go back up to 5/6, or 50 out of 60, then we go back down to 35 out of 60, and then back up to 47 out of 60. Now, I use 60 because that's the common denominator for the first 5 terms. Obviously, if we continued on, we'd have different larger denominators. But my point is here that we go down and then back up, but not to the level we were at previously. And then we go down and then back up, but not to the most recent previous level. So because of this, we will never be any larger than the value of the very first term. That being said, another way to look at this is the following. that for any partial sum of the harmonic series, the same partial sum of the same number of terms of the alternating harmonic series is always smaller, or at least no greater than. In fact, beyond just the very first term, the alternating harmonic series is always smaller. Now, this doesn't necessarily prove anything in and of itself as the direct comparison test goes, because, for one thing, the direct comparison test doesn't apply since one of these is alternating and the other is not. But more importantly than that, the direct comparison test won't help here because we are comparing a smaller series with a larger divergent series. For the direct comparison test to work, the smaller series, the larger series has to be convergent, or the smaller series has to be divergent. Neither is the case here. That being said, if we do make a more generic case here, we can say that in general, the series a sub I is going to be smaller than or equal to the series of the absolute value a sub I. That is to say, if we allow for a series that does have a mix of signs, it must be smaller than or equal to the series that has strictly positive signs. And again, this is easily adaptable for a series whose partial sums end up negative, but we're going to assume without loss of generality that our sums start with a positive term, and therefore the partial sums are always going to end up positive. The fact of the matter is that the alternating signs mean we will always end up with a smaller partial sum in a series that has a mix of positives and negatives than we do in a series that has only a single sign. Now, this can work for us in the direct comparison test if we happen to know that the same sign series, the single sign series, is convergent. So by the direct comparison test, if the single sign series converges, then the alternating or the mixed sign series must converge as well. This concept is known as absolute convergence. A series, whether it be single sign or mixed sign, a series converges absolutely if it converges when it is a single sign. What this means is that it converges regardless of whether its signs are all the same or whether its signs are mixed. However, as with the harmonic series, we saw that it's possible that the series may diverge when it's all the same sign, but the introduction of a mix of positives and negatives can cause it to alternate signs, or can cause it to converge even when the same sign series does not. So a series, which may have a mix of positive and negative signs, converges conditionally if the same sign series diverges. So if the introduction of a mix of positives and negatives allows the series to converge when it otherwise would not, then this is known as conditional convergence, because it only converges on the condition of having a mix of signs. The concept of absolute versus conditional convergence is going to be relevant in upcoming lessons, specifically on the ratio and the root tests. Some examples of this. Suppose we have the series starting at 1 as typical. Suppose we have -1 to the I times I plus 1 over 2 power, and that is over 3 to the I. Now, the interesting part of that exponent is that it actually does not create an alternating series. In order to figure out what the power is, we have to actually input the value of I into it. But the interesting thing is that if I is odd, then I plus 1 will be even. And if I is even, then I plus 1 will be odd. So one way or another, we always have an even, one of the two things, either I or I plus 1 is always even, and therefore this will simplify to an integer no matter what the value of I is. When I is 1, we have 1 times 2 is 2 over 2. And that gives us -1 to the first. So our first term is going to be negative. When I is 2, we have 2 times 3, which is 6 over 2. That gives us -1 cubed, or -1 times or over 3 squared. When I is 3, we have 3 times 4 is 12. 12 divided by 2 is 6. So now we have an even power, and that's going to give us a positive term. So as you can see, this is not an alternating series. And if we continue this out, we would get plus 1 over 81, and so on. This is not an alternating series, but it does have a mix of positives and negatives. Now, what we can look at here is that while this is not alternating, and therefore the alternating series test, AST alternating series test, does not apply, we can still investigate the series where we remove the alternating sign component. The mechanic that makes the alternating sign is in the numerator, and that's all the numerator does, is it's -1 to an integer power. So without that, this is a geometric series. And the fact of the matter is that our value of r is 1/3, and that is less than 1. Therefore, this series converges. So what we've got here is that the single term series, or the single sign series, converges And since the mixed sign series is smaller than it, then the mixed sign series must converge as well. And since it converges whether the signs are mixed or whether they are the same, this series is absolutely convergent. It does not matter whether the signs are the same or whether they are mixed. This is going to converge no matter what. Example 2. In this series, we're going to have, again, starting at 1, we're going to have a simpler alternating sign mechanic in the top. And this time, because it is simply negative 1 to the power of I, it will alternate. And then in the denominator, we'll have the natural log of I plus 1. So when I is 1, we have negative 1 to the first. That will give us a negative sign on our first term. In the denominator, then, we have the natural log of 2. So we have negative 1 over ln 2. And then we're going to have positive 1 over ln 3, and then negative 1 over ln 4, and then positive 1 over ln 5, etc. This being an alternating series, we can use the alternating series test. First, we need to show that the terms do approach 0 as we go, the terms without their alternating sign mechanic. And this certainly will approach 0. Now the second part, which is a little bit tougher, is to show that the subsequent terms are smaller as we go. And we know this much to be true. I plus 1 is always going to be bigger than or equal to I. Therefore, the natural log of the larger value will be bigger than the natural log of the smaller value. And thus, the reciprocals will fit the requirement. Again, the larger the value, the smaller its reciprocal. So if ln of I plus 1 is larger, then its reciprocal will be smaller. So by the alternating series test, this series converges. However, if we then look at the non-alternating version, the same sign version, this can be directly compared to the harmonic series. What we would need to show then is for the direct comparison test to work with the harmonic series, we know the harmonic series is divergent. Therefore, we need to show that the harmonic series is the smaller of the two. We would need to show that for all I, that the harmonic series is the smaller of the two. Well, in that case, we would really be needing to show that I is bigger than the natural log of I plus 1. And that's easy enough to show. If we really needed to, we could get into some algebra with this and show that e to the I is greater than or equal to I plus 1, which certainly is going to be true because we have an exponential function, which is going to grow faster than the linear function, and it starts out ahead. So when I equals 1, we have e to the first is bigger than or equal to 2. 1 plus 1 is 2. And that certainly is true. And from there, the exponential function will grow faster than the linear function will. We then would have e squared is greater than or equal to 3. E cubed is greater than or equal to 4. And it's not even a contest here. The exponential will grow radically more quickly than the linear function. So we have then shown that this is true. So if we know that the harmonic series is the smaller one, then the natural logarithm series is bigger. It must also diverge. Therefore, we can say that this series is conditionally convergent. This series converges only because of its alternating sign. Without the alternating sign, the series would diverge. And that is the concept of absolute versus conditional convergence. There are series that the introduction of a alternating sign allows a series that otherwise diverges to converge, but it's only under that condition. And then there is the possibility that it converges regardless of whether the sign is alternating or otherwise has